Hello everyone, welcome back to the 61-day course for UCEED preparation. As you are aware, in this 61-day series, in this series of 61-day lectures, we are going to cover the entire syllabus of UCEED examination, including part A and also part B, that is including sketching and also the computer-based test part, which includes the logical reasoning, general aptitude and also the design ability test. So in today's lecture, we are going to look into day 37. So as you are aware, we have been following this lecture series for past 36 days. Today, in this lecture, our focus would be on day 37, that is geometry 3-dimensional. In day 36, we have already learned about the 2-dimensional geometry, wherein our focus was specifically on area and area-based calculations. Here in today's lecture, our focus would be on 3-dimensional solids and the calculations related to it, mainly in terms of volumetric basis. So if I give you an overview of the 61-day course, as you are aware, starting from day 1 till day 35, part B, that is the sketching portion, is done, which includes basic sketching techniques, core techniques, and also the applications of sketching into design, which will help you answer the part B questions of your UCEED examination. As far as part A is considered, we are going to do it from day 36 till day 61. In these series of lectures, we are going to cover the entire portion of part A in categorizing into mainly 4 modules, which includes quantitative ability, visualization skills, logical reasoning and design ability. Today on day 36, we are in the first module of part A, that is quantitative ability, and day 37, wherein our focus would be on 3-dimensional geometry. This is Chandar from KP classes, and let us begin our lecture wherein we'll study about the basics of 3-dimensional geometry for your design entrance examinations. So firstly, let me begin by recalling some basics which you might have already studied in your school days itself. We will discuss all the basics right away from the very basic aspects, including the formulae related to cube and cuboid as well, and then we'll take it to the advanced level, which includes also pyramid and tetrahedron as well. And we will, most importantly, once we are done with the basics, we will solve some past seed and UCEED questions so that you have an idea as to what type of questions are actually asked in the paper. So without any further delay, let us look into the basic concepts. I would strongly recommend you to all of you to maintain a proper running notes, the resources like the questions which we will discuss and the resources which we are going to have a discussion on. This will be shared with you on our mobile app. The link for a mobile app is in the description of the video. You can access all these questions over there also for your self-reference. But the pointers which we are making a note of, that is something which you'll need to maintain in a proper running note so that you can revise before your examination as well. So let us look into some basic concepts of 3-dimensional geometry now. Point number 1, let us have a quick discussion with respect to the form of a cube. As you are aware, cube is a 3-dimensional solid which is composed of 6 faces, all of which are square. This is one of the platonic solid. Now I don't want to confuse you with difficult terms and words right away in the beginning. We will discuss about platonic solids after a while, because cube also is a platonic solid. We will discuss about tetrahedron, then I will have a brief discussion on what are platonic solids as well. But as far as the basics are considered, for a cube, if the length of the side, let us say, is A, there are 2 points you can remember: surface area and volume. This might sound very silly and very simple because it is just a simple cube which even someone from 5th standard would know. But moving further and applying these onto questions, that's of key importance for SEED and UCEED examination. So it is important to recall even the basics. So let me make a note on the formulae. As far as the total surface area of a cube is considered, there are 6 faces, all of which are squares, all of which are a square of area a square, so 6 into a square. As far as the volume is considered for a cube, it would be a cubed, a into a into a, wherein a is the length of the side of the cube. So if you look into cuboid as well, I'll just write it over here itself, cuboid. It is basically a 3-dimensional solid which is obtained by extrusion of a rectangle of length L and breadth B. If you extrude it to a height h, you would be getting a cuboid wherein the volume of the cuboid is L into B into h. And if you look into the total surface area of a cuboid, it will be 2 into LB, because there are 6 rectangular faces, 2 of them are of dimension L into B, 2 are of size B into h, 2 are of size L into h. So the total surface area of a cuboid would be 2 into LB plus BH plus LH. That is something which are very basic points with respect to cube and cuboid. Moving on to point number 3, let us have a discussion on cylinder. Something common in cube, cuboid, cylinder, all these are solids which are generated with extrusion. What do we mean by extrusion? If you have a two-dimensional plane extruded to a particular height, then that is called as a prismatic solid. All these are prismatic solids because they're obtained by extrusion. So there is a generalized formula also for all the prismatic solids. But first let us have a discussion on the cylinder part. So cylinder is basically an extrusion of a circle. So if you have a circular form and extrude it into a height h, let us say this is a circular base of radius r. If you extrude this circular base to a height h, you would be getting a cylinder. And what would be the volume for cylinders? You can remember volume of cylinder. In fact, for cube and cuboid also it is the same. Area of base multiplied by the height of extrusion. Area of the surface which is being extruded multiplied by the height. So what is the area of the surface which is being extruded? Here it is a circle which is being extruded. The area of that circle is pi r square. And the height of extrusion is h, so pi r square into h will give us the volume of the cylinder. Whereas the surface area, it's not very important to remember the surface area of a cylinder. However, just because we are discussing it is just one formula, so let me just mention you the curved surface area of the cylinder, that is basically 2 pi r h. Whereas there are two circles also at the base and the top, so 2 pi r square plus 2 pi r square. So 2 pi r h plus 2 pi r square, that would be the total surface area of the cylinder. You can take 2 pi r common, 2 pi r into r plus h. That would be the formula for the total surface area of the cylinder. If you just want the curved surface area, it would be 2 pi r h. That's with respect to point number 3, that is cylinder. Now let us discuss about the generalized formula for any type of extruded solid, which basically is a prismatic solid like I told you. So let us say this is a random shape, something like this. And if you are extruding to a height h, let us say this is a random shape which is being extruded to a particular height h. The height of extrusion, that is h. This area, if it is a, the volume of this solid also can be calculated as area of the base which is being extruded multiplied by the height of extrusion. So volume of any prismatic solid. When I say prismatic solid, we're talking about the solids which are being extruded. So this is solids which are created by extrusion. There are past UCEED and CEED questions which are three-dimensional forms obtained by extrusion. For example, there was a question once wherein the base was in the form of a star, something like that. And if you are extruding it to a height h, even for this the volume would be the same. Even for this, the volume would be the same, area of that star multiplied by the height of extrusion. Now, when we come to that question, we will have a discussion of how can you find out the area of a star. We'll have a discussion on it. It's based on simple equilateral triangle concept itself. And we already have done in-depth questions already for two-dimensional area-based questions. Like you might have remembered about the regular hexagon we had a discussion on. It is based on the similar concept. So it was very simple and easy to understand. You need not worry about it. But I was talking about volume of any solids generated through extrusion. The formula is simple. It is area of the base. When I say base, we are talking about the area which is being extruded. In this case, it is star. In this case, it is that random organic form. In this case, it is a circle. In this case, it is a rectangle. Area of this rectangle is L into B. Multiply that with the height. Here, the area of the base is A square. Multiply it with the height. Height also is already A. So in cuboid it is easy to visualize. L into B is the area, then multiplied with the height. Here pi r square is the area multiplied with the height, pi r square into h. So volume is always area of the base multiplied by the height of extrusion. When I say height, we are talking about the height of extrusion. Extrusion is basically extending it along that particular surface. So that's a generalized formula you can remember with respect to solid. So let me write this. We are following a point by approach, point-wise notes. So 1, 2, 3, and then this is point number 4. Let us now move on to point number 5, wherein we'll have a discussion with respect to sphere and hemisphere. There are questions in past CEED, UCEED also on sphere, hemisphere. So let us have a quick recall of those basics as well. As far as sphere is considered, Sphere is basically a set of points in a space. It is a three-dimensional form generated by joining all the points in a space which are equidistant from a center. So you have a point and all the points in the space which are equidistant from that center, they will be forming a three-dimensional form that is basically a spherical solid. So if this is a full sphere, let us say the radius of the sphere is r. If you know the radius, so there's only one metric which you need to know for spheres, just the radius, that's it. Just like cube, in cube also you just need one metric, that is length of the side. Even in sphere it is the same. So if the radius of the sphere is r, then the volume of the sphere is given by 4 by 3 into pi r cube. If you just want the surface area, I'll mention it, but not very important it is. That would be 4 pi r square. That's the area, surface area of a sphere, but it's optional. But remembering the formula for volume is very important for your examination. There have been multiple questions in past UCEED papers wherein you'll need to apply the formula for volume of a sphere, that is 4 by 3 pi r cube. Now moving on to hemisphere, it would just be the half of it. If you have understood what is prismatic solid, we had a discussion on. I would ask you a simple question. If you're following a lecture series, please comment down your answer on it. Do you think sphere and hemisphere are prismatic solids obtained with extrusion? Yes or no? So basically three-dimensional solids in geometry, they can be created in multiple ways. They can be either created by extrusion or they can be created by surface of rotation. You can take a surface and rotate it. Like sphere, how do you form it? You take a circle, rotate it. You take a circular plate, rotate it along an axis. You'll get a solid which is formed. That basically you'll have a sphere. So can you comment down, do you think you can generate sphere and hemisphere with extrusion also? Yes or no? It's a very simple question, and yes or no. So I would that will encourage us also to know if you're following our series and our lectures, are they comprehensible to you in an ideal manner or not. That will help us understand. So hemisphere I was talking about. Hemisphere is basically half of a sphere. It's if you cut the full sphere into a half, you will be getting a hemisphere. And if the radius of the hemisphere is r, same thing again, volume, it will be half of this, 1 by 2 into 4 by 3 into pi r cube. That would give us 2 by 3 into pi r cube. So that would be the volume. Now if you wish to know the surface area, the curved surface area will be half of 4 pi r square. So 2 pi r square will be the curved surface area of a hemisphere. You have a circular plate at the bottom also, so add one more pi r square. The total surface area will be 3 pi r square. I'll just mention it. The curved surface area, that is just the spherical curved surface area, that would be 2 pi r square, wherein the total surface area, that would be 3 pi r square, because one more pi r square at the base plate, circular plate, that adds up into 2 pi r square. That's the formula for sphere and hemisphere both together. I'm just writing it under point number 5. Moving on to point number 6. Now this is where we are moving into solids which are not created by extrusion. So starting from this 5th point, so let us now move on to the 6th one, that is about cone. So we just have 2 more things. We'll discuss about cone and a pyramid. So under pyramid itself there are variations we will have a discussion on. We'll discuss about a square based pyramid, a triangular based pyramid, and so on. So firstly, with respect to cone is basically a solid generated by rotating a triangle along its height. If you take a triangle, now how do you generate a cone? If you take triangle, right angle triangle, let me take. Along this line, along this axis, if you rotate it in 3 dimension, you will be generating a path, a solid that forms a cone. That's the origin of this shape cone. However, let us focus on the basic formula which you have to remember, mainly volumetric ones. In terms of volume of a cone, simple and straightforward. It would be 1 by 3 into area of base into height. For cone and pyramid it is same. It will be 1/3 of the volume of a, so for cone for example, the volume of cone will be 1/3 of the volume of a cylinder of same height. If I imagine this cone to fit into a cylinder like this. Now, what is the volume of the cylinder? We already have studied, because it's a prismatic solid obtained by extrusion, area of base multiplied by height. Area of base, if the base radius is r, if the height is h, then the area of the base, that would be pi r square. Height is h over here, I'm assuming height of h. The volume of the cone, or let me just recall volume of cylinder like we discussed already. It would be area of base multiplied by height, pi r square into h. That's the formula because it's a prismatic solid. Whereas volume of the cone, it will be 1 by 3 into area of base into height. So you can remember it like this: 1/3 of the volume of cylinder of same height. So if you're talking about the cone, that's the formula for the volume of the cone: 1/3 of the volume of the cylinder of same height. That's for cone. That's point number 6. Remember one more term: this particular height along the center, that's called a space height. The h which you're taking over here, this is the space height of the cone. Slant height would probably be calculated along the generator. So that curved surface which you get for the cone, there are two surfaces. How do you get a cone? There are two surfaces. You have a base, circular base. The curved surface on the top, that's called as the generator of the cone. Along the generator, you will have the slant height. This is the space height. Slant height is along the generator. What is generator? The external surface, this particular surface of the cone, which is curvilinear, that's called as the generator of the cone. So that's number 6. Moving on to point number 7, let us discuss about pyramid. First, let me tell you a generalized formula for pyramid, then we will talk about some specific cases of pyramids. So firstly, with respect to the generalized formula, what exactly is a pyramid? It will have a polygon in the form of a base. It can be a square, it can be a rectangle, or it can also be a triangle as well if it is a tetrahedron. So let us consider a rectangular base. If you join these to the top, that's how you get a pyramid. Now if the dimensions of the pyramid, let us say this is L, this is B, and let us say the space height, again here also, just like for cone, here also you will be having space height and slant height. Slant height is along the faces. Along the triangular pyramid is generally formed with a polygon and triangular faces on the top. If it is a triangular base pyramid, you will have 3 triangular faces on the top also. If it is a square base pyramid or a rectangular base pyramid, you will have 4 triangular faces on the top. If it is a pentagon pyramid, pentagon base pyramid, you will have 5 triangular faces on the top. If it is a hexagon base pyramid, you will be having 6 triangular faces on the top connecting at a vertex. So the number of triangles connecting at a vertex in pyramid will depend on the number of sides in the base polygon. Now the volume formula is same for all these types of pyramid. So for any type of pyramid, now you need to know the space height also here. You need to know the dimensions of the base. If it is a regular polygon like square or pentagon or hexagon, you need to know the length of the side. In this case, I'm not taking a regular polygon, I'm just talking about a rectangle here, not even a square. So I have taken length and breadth both. The space height is h. The formula is pretty simple, just like cone, 1/3 of the volume of a cuboid of same height. Imagine the cuboid into which this pyramid can fit into. So that would basically be a cuboid of length L, breadth B and height h. What will be the volume of that cuboid L into B into h? It will be, so volume of pyramid, any pyramid, it would be 1 by 3 into area of the base multiplied by height. In fact, if you extrude it, the form always for solids made of extrusion, it can be a pentagonal prism also. If you have a pentagon at the bottom, if you extrude it to a particular height, the volume of this will be area of the pentagon multiplied by height. Whereas if you are having a pyramid of the same base, instead of prism, if you are having a tip over here, all these edges, if you'll be basically getting a pentagonal base pyramid. The volume of that pyramid will be 1/3 of area of base into height. So it's the same for any shape you take. Just a second. For any type of shape you take, it is the same formula. For prismatic solids of extrusion, it is area of base into height, whereas for pyramid, it would be 1/3 of the area of base into height. So in this case, if you apply this formula in this particular case, what would be the volume formula? It would be 1 by 3 into area of the base is L into B multiplied by H. If it is a square base, if you have a square base pyramid with side A, then the volume for such a pyramid will be 1 by 3 into a square into h. 1 by third of area of base into height. If you are having a let us say triangular base pyramid, let us say an equilateral triangular base pyramid of side A, then the volume formula for it will be 1 by 3 into area of the base, area of an equilateral. I'm talking about equilateral triangle. Had it not been an equilateral triangle, then it would be 1 by 3 into area of the triangle, that is half into base into height of that base triangle into height. So 1 by 3 into, in this case it's an equilateral triangle, so 1 by 3 into root 3 by 4a square, that's the area of an equilateral triangle into height. 1 by 3 into area of base into height. That's the formula we'll be having. So if you simplify this, what's the volume for a equilateral triangular base pyramid comes out to be, you can simplify it further, root 3 by 4 a square into height into 1 by 3. That would basically be giving you a square into h divided by 4 root 3. That's what you will be getting. Furthermore, moving further, we can actually derive the value of h in terms of a and simplify this formula even more. For now, let me not confuse you. Let me leave it over here. We'll come back to the discussion on this point in a while. Now, the point we need to understand is there is a particular name we use for this equilateral triangular base pyramid of side A, and that is called as a that's called as a tetrahedron. A pyramid which you get with an equilateral triangular base, not only an equilateral triangle, in fact all the remaining edges also should be triangles. So let us discuss, it's a type of an equilateral, you have an equilateral triangle as a base, and also the remaining 3 edges on the top should also be of same length. That's called as a tetrahedron. So let us have a detailed discussion with respect to tetrahedron. Questions have been asked, in depth questions have been asked in CEED, UCEED from tetrahedron also. So we'll have a discussion with respect to the center of the tetrahedron in further details, and then we'll move towards practicing the questions. So that will be the last point. So let us have a discussion with respect to this solid of tetrahedron. Firstly, what is a tetrahedron? This is a solid which is formed with 4 equilateral triangular faces. Tetrahedron has 4 equilateral triangular faces. It is a triangular, it's a type of a equilateral triangular base pyramid. It's an equilateral triangular base pyramid wherein it overall has 4 equilateral triangular faces. Let us visualize this solid first. So if you take an equilateral triangular base, have a vertex, join it to all these 3 edges, this solid basically will be having a total of 4 equilateral triangles, 1 at the base, 3 at the top. This is number 2, number 3, and the 4th one at the back. So there are 4 equilateral triangular faces forming this particular solid, which is called as tetrahedron. And remember, tetrahedron is considered to be the most basic of the 5 platonic solids. There are only 5 platonic solids, of which tetrahedron is one. So for people in the area of design, it is very important. Geometry is one of the intrinsic aspects of your study of design. It is important to visualize various solids, and understanding platonic solids can be interesting also. So let me briefly tell you what are platonic solids. There are only 5 in all the 3-dimensional solids. There are just 5 solids which follow the simple rule, common rule, which make them to be termed as or classified as platonic solids. First, let me tell you about the rule, then I'll tell you about the names of those 5 platonic solids. So firstly, what is the rule? Platonic solids are basically regular polyhedron. They are regular polyhedron. Actually, polyhedra is a plural. If I write it in singular, each of the platonic solid is a regular polyhedron. When I say polyhedron, regular polyhedron. Polyhedron is basically a 3-dimensional solid formed by adding various polygons, adding various surfaces to create a solid. That's called as polyhedron. Regular polyhedron is something where all the faces are same, congruent, absolutely same. Like for example here, a tetrahedron, I told you, has 4 equilateral triangular faces. Any face you take, it is the exact same equilateral triangle of the same length of the side A. So Platonic solids follow that first rule, that they have to be regular polyhedron, that is, all the faces of that solid should be exactly same and congruent. That is number one. The second rule which is required for a three-dimensional solid to be called as a Platonic solid is, at every vertex the number of faces meeting should be same. Number of faces meeting at each vertex is same. Same number of faces should meet. Just these two simple rules. Any 3D solid, if it is following these two rules, it can be called as a Platonic solid. And I told you, in the universe of 3D geometry, there are just 5 Platonic solids which follow both these rules. That is, first, they have to be a regular polyhedron with same faces, all congruent. Second, the number of faces meeting at every vertex should be exactly same in number. Like, let me take the example of tetrahedron. Can you count and tell me what are the number of faces meeting at this top vertex? One face over here, one on the right, one at the back. There are 3 faces meeting at this top vertex. The second vertex, 1, 2 and 3 again. One at the base, one at the top, one at the rear. 3 faces are meeting at this vertex. At this vertex, if you see, there is one face over here, the second face over here, and the third at the base. There are 3 faces meeting at this vertex. Same thing for this vertex. At each vertex, there should be same number of faces meeting, and each of those faces should be same regular polyhedron. So regular polygons, basically of same size and shape and congruency. So that's when it will be called as Platonic solid. And I told you there are 5 such solids. The most simple of all is tetrahedron. Like I told you, that's the first Platonic solid. Other than tetrahedron, let me mention over here tetrahedron. This is formed with 4 equilateral triangular faces. Then you have cube, which is formed with 4 squares. Now squares are also same congruent faces, and at every corner of the cube also you will have same number of surfaces meeting. So at cube, so 1, 2 and 3. There are 3 faces meeting at every corner, at every vertex. Same rule follows for cube. All the faces are same and the number of faces meeting at every vertex is same. So cube is the second Platonic solid. There are 3 more Platonic solids which follow these rules after just like tetrahedron. You would be having an octahedron, which has a total. So tetrahedron has 4 faces, cube has 6 faces, octahedron has 8 faces. Then you would be having a dodecahedron and icosahedron. These two, dodecahedron, which has total of 12 faces, and at every vertex you'll have the same number of surfaces of faces meeting. And finally you have icosahedron, which actually has a total number of 20 faces. So these are the only 5 Platonic solids in the universe. So you can remember the rule, and also, so that's just an additional add-on. But let us focus on tetrahedron and its geometry in brief detail again. Let us look into the formulae with respect to tetrahedron as well. So for that I have composed, so that it is easy for you to visualize, I have included a picture of tetrahedron and various pointers of geometry. I'll talk about some important points which you have to remember from exam point of view. Whatever formula I'm discussing over here, make sure you maintain a note of it. This will be the last point of discussion. We'll move towards practicing different models of questions. Now in the examination of UCEED, from 3-dimensional geometry, there are different models of questions. There are models of questions which are directly based on 3D geometry. There are models of questions which are based on form generation of 3-dimensional geometry. There are also questions based on packaging, because that also involves 3-dimensional geometry, packing some particular, designing or finding out the volume of packaging or ideal minimum volume required for packaging. Such questions have been asked in the past and will be asked in the future as well. So for that, these basics are important. So using these basics, we'll cover all the possible models of 3-dimensional geometry based questions which can be asked in your UCEED paper. I was telling you about the tetrahedron. We are going to discuss some pointers of its geometry. So if you look into the tetrahedron over here, it has a total of 4 equilateral triangular faces. Now this red dot which you see over here, that's basically the center of the base triangle, the base equilateral triangle. You can assume any triangle to be at base. Taking that as the base, there will be a center point of that particular face. Joining that center point of the base to the top vertex, you'll get height, that is called as the space height of the regular tetrahedron. So space height of the tetrahedron. So what you see over here in this picture, the red line, that denotes the space height of the regular tetrahedron. That denotes the space height of the tetrahedron. Now this one, this yellow triangle which is formed, how is this triangle formed? Just have a look at it. Understanding this triangle is important to know the other parameters of tetrahedron. So how is this triangle formed? It is formed by taking one of the edges, one edge of the tetrahedron, then one height of one of the face, height of the other face. Height of two faces, two equilateral. This is one of the height of the base equilateral triangle. This is height of the side face of the equilateral triangle, and one edge of the tetrahedron. That is the base triangle which we are going to use to understand various terms of various distances of tetrahedron. So in this particular picture you can see the space height. So let me first mention, first important formula for you to remember is the space height of the tetrahedron. Space height of the tetrahedron is given by root 6 upon 3 into A. I told you already we will simplify the formula for volume of tetrahedron using this further mode. We have written already one formula for volume of tetrahedron. What was that? 1 by 3 into area of the base equilateral triangle, that is root 3 by 4a square into height. Let me just go back and show you quickly so that you are not getting confused over here. Volume of the tetrahedron is 1 by 3 into area of the base equilateral triangle, that is root 3 by 4 into a square multiplied by the height. So here there is a formula which we have for height now. Root 6 upon 3 into A, where A is the length of the side. That we can substitute over here and further simplify this formula, and we'll come back to that in a while. First let me complete all the important points which we'll discuss over here. So what is A in this particular case? So space height, we are denoting it by H. A is nothing but the length of the side, length of the edge, any edge. In a tetrahedron, you would be having a total of 6 edges, 3 edges at the base, 3 at the top. All those edges will be of same length A, that is basically a tetrahedron, and the height of it will be root 6 upon 3 into length of that edge A. That's first point you need to remember. Now coming to the insphere and circumsphere, there have been questions on insphere and circumsphere of tetrahedron also, so let us have a discussion on it. If you look into this tetrahedron, circumsphere is that sphere which is basically contained outside the tetrahedron, whereas insphere is the maximum possible size for a sphere which can fit into the tetrahedron. I'm repeating again, circumsphere is the smallest sphere which can encompass the tetrahedron, which touches all the edges, the vertices of it. Every vertex is touching that circumsphere. Insphere, on the other hand, that is the largest size of a sphere which can fit into the tetrahedron. It will touch every of the triangular face. Every equilateral triangular face will touch the insphere. That is something you can remember. For insphere and circumsphere, you can visualize that in this 3D solid. It is important for us to know the dimensions of the radius of insphere and radius of circumsphere. I'll tell you the formula, I'll tell you what their lengths are, but before that, if you can visualize over here in this diagram, it will be better for us to understand the insphere radius and circumsphere radius. If you look into this picture, the same triangle formed with one edge and two heights of two bases, that is shown over here. And if you look into the insphere, that insphere touches every triangular face. So it will basically touch this particular height, it will touch both the heights, it will not touch the edge. The insphere will not touch the edge, but it will touch these. If I draw an insphere over here, it would be something over here like this. It will touch these faces and the heights. It will touch these heights, but it doesn't touch the edge of the tetrahedron. Now coming to the circumsphere, it will touch the vertices, but it will not touch this particular midpoint. This point over here, if you observe carefully, this point is nothing but the midpoint of this triangle over here. So it doesn't touch that. It will just touch the vertices. So that's how you can remember. Now coming to the radius, the red line over here, this one from the vertex to the centroid. So this is called the centroid of the tetrahedron. Again, just like how we discussed for equilateral triangle in the previous lecture, day 36 of two-dimensional geometry, we have studied about the equilateral triangle, if you remember. In that, I told you the incenter, the circumcenter, and also the centroid are all same, right? So all those 3 points will coincide for an equilateral triangle. Similarly for tetrahedron also, the center of the insphere, the center of the circumsphere, and centroid of the overall tetrahedron all coincide. So from the centroid to the vertex, that is the radius r of the circumsphere. So let me mark the radius of the circumsphere as r, which is from center to the vertex. So what is circumsphere's radius? It will be centroid of the tetrahedron to the vertex, any vertex. Centroid to any of the vertex, that is radius of circumsphere. Whereas radius of insphere, it is centroid to the face, or it is basically to the height of that triangle. You can say the triangular face, that is the triangular face. So insphere radius, if I denote it by small r, this is the distance from centroid to the equilateral triangular face. From the in-center, you can see in this picture over here, from the vertex to the centroid, that is capital R, that is radius of the circumsphere. In-sphere radius is over here, the remaining part of the height. The remaining part of the height is basically from the centroid to the face, it is touching this height of the equilateral triangle, the equilateral triangular face. That's the reason I've written over here, insphere is centroid to the equilateral triangular face. So what are these dimensions? What are these distances? Let me mark over here. For circumsphere, the radius of the circumsphere is just like this, √3 by √6 by 4 into a it is. That's the radius of the circumsphere, whereas radius of the insphere for any tetrahedron, in all these a is the same, it is length of the edge of the tetrahedron. Radius of the circumsphere of a regular tetrahedron, that will be √6 by 4 into a, whereas the radius of the insphere, that basically will be √6 by 12 into a. That's the value for the radius of the insphere. One interesting point, a last interesting point, actually there are 2 points. We'll look into the relation between these terms, and finally we'll need to substitute this and derive a simpler formula for volume, I told you. So we'll discuss that as the last point. But here if you observe, capital R is from vertex to centroid, that is capital R. From centroid to the base equilateral triangle, that is small r. If you add capital R and small r, you should be getting the space height of the equilateral of the tetrahedron. You can check that from this formula also, capital R plus small r. Let us try and see if we are getting the same formula for H or not, because like I told you, H is capital R plus small r, where capital R is radius of the circumsphere, small r is the radius of the insphere. So let us add the circumsphere radius and insphere radius. You will get √6 by 4 into a plus √6 by 12 into a. So that we can easily add. I'll be multiplying with 3 over here and also here. If I multiply numerator and denominator with 3, we'll get 3 √6 divided by 12 over here. Now denominators are same, you can add these values directly. 3 √6 plus √6, you will get 4 √6 divided by 12 into a. 4 3 times will cancel out. You will be getting √6 by 3 into a, which is the same formula we saw for space height of a tetrahedron. So remember, for a regular tetrahedron, the space height will be equal to the radius of the circumsphere plus the radius of the insphere, and the formula will be √6 by 4 into a for the radius of the circumsphere, √6 by 12 into a for the insphere, √6 by 3 into a for the space height. All these three formulas are equally important. That brings us to the last point for tetrahedron. Let us discuss the important formula for tetrahedron. That is, for a tetrahedron, 2 things to remember. Surface area, just like how we discussed for all other solids. For tetrahedron, what is the surface area? There are total of 4 equilateral triangular faces. So the surface area will be 4 into area of each equilateral triangle. From the past lecture, you might remember, area of an equilateral triangle is √3 by 4 into a square. So simply the area of the surface area of tetrahedron is very simple, straightforward, direct. That would be √3 into a square. Moving on, volume. Volume of a tetrahedron, we already have written down the formula. It will be 1 by 3 into area of the base. Area of the base is √3 by 4 a square into the space height of the tetrahedron, and we already know a space formula for space height of the tetrahedron. Let me substitute that over here. 1 by 3 into root 3 by 4 into a square. In the examination, for such wherever questions which involve such complex formulae involving square root and all, square root 3, square root 6, you will have a calculator on the screen. You are not allowed to carry your own calculator, but you'll have an on-screen calculator in the examination which you can use in order to solve. So root 3 by 4 into a square into height, the formula is root 6 upon 3 into a. Now if you simplify this, you can separate out the a cube separately. Other than that, in the numerator you will have root 3 into root 6. In the denominator you will have 3 into 4 into 3. Let me simplify this value. So if you cancel out in the numerator, root 6 can be written as root 2 into root 3. So this further can be written as root 3 into root 3 into root 2 divided by 3 into 4 into 3 into a cube. Now root 3 into root 3, that is 3. That and this one of the 3's will get cancelled out. Other than that, 4 basically is 2, it's like 2 into 2, and every 2 you can write it as root 2 into root 2. So if you simplify that, basically in the denominator you will be left out with 2 root 2. If you want, I can write it clearly. In the numerator you are left out with root 2. In the denominator you are having, I can write 4 as root 2 into root 2 into 2. I can simplify and write it like this. 4, I can write it as, I can disintegrate into root 3 and root 2 into root 2 into 2 into 3. So this root 2 will get cancelled out. What I will left out over here? 2 root 2 into 3. That will be 6 root 2. So simplifying this, the final formula which you are basically getting is a cube divided by 6 root 2. A cube divided by 6 root 2. That's the formula for the volume of a tetrahedron, which you can remember. A cube divided by 6 into root 2. That's the formula for the volume of a tetrahedron, which has been simplified by substituting the value of height. So ultimately, what are the values you have to remember for regular for a tetrahedron, which is the basic of the platonic solids? Number 1, you have to remember the formula for the space height. Number 2, you have to remember the distance of the circumsphere, then the in-sphere radius, and the relation between these three. I told you the space height is in-sphere radius plus the circumsphere radius, and I told you about the formula for surface area, root 3 into a square, whereas the volume, that is a cube upon 6 root 2. You need not by heart this, you can derive like we have done over here if you get a question in the examination. All you need to remember for the exam, other than the points you have discussed in equilateral triangle, you just need to remember 1, 2 and 3 and the relation between them. It might sound a bit difficult when you look at it for the first time. Spend some time, look at the pictures, visualize it, write the formula for yourselves on a book, practice once after writing down in your study material and on your self-read notes. That will give you a lot of confidence and you can easily answer the questions in that area. So with that understanding, let us now look into the application part. So that was the basics with respect to understanding various formulae. Let us practice some questions with respect to the three-dimensional geometry from past UCEED and CEED question papers. So let us begin with this question over here. This is a past UCEED question from the year 2023. Let me take you through the question. The image shows profile of a blade which is designed to turn a wooden block rotating about the axis PQ. So this is a blade, they are saying that blade will rotate. Blade is going to rotate along the axis PQ. So if you place a wooden block and then turn this blade, it will create a solid, they are saying. Calculate the volume of the turned wooden block between P and Q. Consider the value of pi to be 22 by 7. Now imagine if this is a blade and if you're cutting a wooden block with this blade, what is the end output? You would be basically getting a 3D solid of that wooden block, something like this. Right? This is what you'll get by rotating, because it's being rotating along the axis PQ, they are saying. So this will be that axis PQ. Now, what kind of solid is this? It is a combination of cone and a hemisphere. So this part of it is a cone and this part of it is a hemisphere. We'll need to add the volume of the cone and the hemisphere. The dimensions are marked on this grid over here. First, let us find out the volume of the cone, just the cone part. I'll just mark it over here for the cone part. you just need to know two things in cone to find out the volume. One is height and the other is the radius r. So what is the volume? So height and radius, we'll look at the picture. But what is the formula for volume in cone? It is 1 by 3 into pi r square into h. So this will be 1 by 3 into pi. They have told us to take 22 by 7. If you want, I will just write it as 5 for now. We'll substitute the value at the end so that it is easy for us in the calculation. Pi into r square. What is r of the cone? The cone radius is this one, this distance. That is basically 1 unit. So this is r is 1 square into the height h. What is height of the cone? You can see from here till here, this distance 1, 2, so it's this 1, 2, 3 and 4. So this is 4 units. So you will multiply it with 4 over here. So what is the volume of the cone you are getting? Yeah, I'm getting it as 4 by 3 pi. 4 pi by 3, that's the volume of the cone. I'll write it as VC, volume of the cone. Now coming to the hemisphere, it is important that you observe carefully that it is a hemisphere or not. If you observe this distance and this distance, they are exactly same. So obviously when you rotate it, it will also form a same distance on the same radius. So it will form a hemisphere. What is the radius of hemisphere in each direction? This is also 2 units, this is also 2, this is also, the radius of the hemisphere is basically 2. What is the volume of the hemisphere? It is 2 by 3 into pi r cube, wherein r is 2 over here. So this will be 2 by 3 into pi into 2 cube. 2 is the radius. 2 cube is basically 8. So this is coming out to be 16 pi by 3. That's the volume of the hemisphere. What is the total volume you are getting for the given wooden block solid now? This plus this. So 16 plus 4 will give us 20. 20 pi by 3 will be the final answer. So the volume, final volume is equal to 4 pi by 3 plus 16 pi by 3. 4 pi plus 16 pi, that is 20 pi. The numerator is 20 pi divided by 3. You can use your calculators. Pi is substituted to, should be substituted to 22 by 7. So it's this way, 20 by 3 into 22 by 7. So you can use your calculators. You can use it quickly and you can solve it. If I just, for the purpose of this question, if I solve it quickly, 20 into 22 is in the numerator, divided by 21 in the denominator. That's coming out to be 20.95. That's the answer which we are getting. I see if there's any, if I have the official answer key. Let me just see. This is coming out to be 20.95 from the calculator. That's the correct answer as per the official answer key. You can check the official answer key on the website of UCEED itself. So 20.95 answer will be in range in such cases. Few digits, it's like something like 2.9 to 20.9 to 21, something like that. They will give you a slight range, so you need not worry. 20.95 is the correct answer for this question. So that's about the first simple straightforward question. All that we applied is just volume of cone plus volume of hemisphere. That's all which we have done in this question. The next one. Now this was the shape I talked about when I was explaining about prismatic solid, if you remember. So let us discuss about it. The blue colored liquid is used completely to make a star shaped jelly using the mold shown on the right. What is the value of x in centimeter? Ignore the wall thickness of the mold and consider the value of pi to be 22 by 7. So basically you have some blue liquid. The volume of the blue liquid you can find out from volume of cylinder. That jelly you pour into this star, they are telling you pour it completely into this star shaped jelly, jelly basically. They are asking us the value of the x. From the diagram you can see all these dimensions are same. Ideally they should have mentioned it. They have not mentioned, but they have shown just that all these values are same. It looks same, right? So it's a star with all the edges of same value x. The height of the star is basically 4 centimeters. So it's based on equating the volume. First you need to find out the volume of the cylinder. Equate it with the volume of the star shaped mold. So first let me find out what is the volume of the jelly we have. What is the volume of the cylinder? Let us first do that. Volume is equal to volume of cylinder, you know, it is area of base into height. That is pi r square, pi into square of the radius of the base into height. So how much is this? Pi they have, for now they have given the value of pi to be 22 by 7 into the base radius is 6 centimeter, base diameter is 12. So the base radius will be 6 centimeter. So this will be 6 square into height is given as 6.6. They have given 3.8 into 3. Probably that will help us simplify the question moving further. If you want, you can use that also, because root 3 will get over here because it has equilateral triangles. That root 3 actually moving ahead will get cancelled. That's the reason they have given it. So if you want, you can do that also, or you can directly take 6.6, whichever you're convenient with. Let me take 3.8 into root 3 because they have given that value to me. So in terms of root 3, what is the volume? We are getting volume of the cylinder 22 divided by 7 multiplied by 36 multiplied by 3.8. I'm getting the volume of the jelly to be, I have left out that root 3 because I know it will get cancelled out. It involves, because you know in area of equilateral triangle you will get root 3 by 4a square. So that's the reason we will leave out that root 3 for now. You will get 429.94. If you want, you can round off further, 9429 into root 3. Now leave this volume aside. The important thing in the exam is also the speed. You should be confident and quick enough to answer the question. You'll have a calculator, but you have to be very speedy in answering, very quick in answering the questions. The best thing is the numerical part is something which is scoring in your examination. That is something which which has least confusion. You might have seen the past CEED, UCEED papers. When you have options, it would be even more confusing in many cases. So coming back to this, the mold now, let us equate with the volume of this mold. I told you, is this mold a prismatic solid, yes or no? Obviously it is a prismatic solid because the base shape is a star. You extrude it to a height of 4. So what is the volume of this star? Volume of the mold is equal to area of the star multiplied by 4 centimeters multiplied by the height of it, height of extrusion. So what will be the, so volume of the mold should be this one. Whatever volume of jelly you have, that should be equal to volume of the mold also. So if I equate that over here, 429.9429 into root 3 is equal to the area of the star multiplied by 4. Now what is the area of the star? Let us understand that. Let me, we'll go back to the calculation, but first if you observe the star over here, this is the shape. You get each of these faces are equilateral triangle, the side is x, and in the center also you will get a regular hexagon. And we already discussed in 2D geometry how you can divide a regular hexagon into 6 equilateral triangles. So the same equilateral triangle, how many equilateral triangles are together forming this star? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. There are 12 equilateral triangles all of same dimensions that is basically forming this star. So what will be the total area of the star? 12 into root 3 by 4a square. That's the standard formula for area of an equilateral triangle. So let me substitute that over here. 429.9429 into root 3 is equal to area of the star is 12 into root 3 by 4 into a square. Length of the side is x here. So let me write it as x square into 4. This 4 and 4 gets cancelled, root 3 and root 3 gets cancelled. I am getting the value of x square is equal to 429.9429 divided by 12. That's the reason I left root 3. I know that it will get cancelled out because from the understanding of the picture itself, it is clear and evident that root 3 has to come into the formula. So, and that's the reason they have also shown it. So 429.9429, divide that by 12. You will get 35.82 or 35.83. That's the dimension in centimeters. All these values have been in centimeters. That's the answer for this question, 35.83. So the actually that's x square. That's so it's important also to. Is this the final answer? This is the value of x square. They have asked us to calculate the length x. So don't leave out the final step. Length x is equal to square root of 35.83. That will come out to, we can use your calculators, square root of 35.83 coming out to be 5.99. 5.99 centimeters. That would be the final answer. Answer will be in the range plus or minus 0.01, 0.02. That's fine. They will give you a bit of range for leeway because it involves a lot of rounding of root 3 pi. Whenever root 3 pi are involved, obviously the answer will be in decimal places and there can be rounding of errors. So they will give you an answer in a range. Marks will be given to anyone who will answer within that defined range. Ideally, it is always better that you round off properly to 2 or 3 decimal places after the decimal point. That way you will stay within the range. So that's the answer. So simple concept. There's nothing difficult we have applied over here. It is just based on simple rule of area of base into height. That's it. Here also we have applied area of the circle into height, area of base into height. Here also we have applied area of base into height. Just that you need to visualize the given base, the star form, and how that area is 12 times the area of each equilateral triangle. Each equilateral triangle is root 3 by 4a square. If you don't remember these basics, go back and check the previous lecture. In day 36, we have discussed this in detail and practiced a lot of questions on equilateral triangle too. Now, as you are aware, it is very important that you have a sufficient practice of the concepts we are discussing. All these questions for your reference have been uploaded on our app. Other than that, you have free access to tests also on our app. So for these free resources, you can download our app, KP Exam Prep app, the link for which is in the description of the video. Once you download and sign up into our app, you will find the option of store over here. If you click store at the bottom, you'll find the codes. So there are various courses we offer. So you can check UCEED course, which we are dealing with right now. If you select the UCEED course, you have various UCEED courses. You can click on the 61-day course option and purchase the series, lecture series right away from there. UCEED 2025 lecture series over here. So from that you can purchase it. Other than that, if you want to access the free resources, you need to click on these 3 horizontal lines which you see on the top left corner of the screen. That will open up the side tray. In the side tray, you have an option of free material. If you observe, there's an option for free material over here. So click on the free material. You'll find various free documents, various free videos, various free tests related to the preparation of UCEED examination. If you want access to everything, you can purchase the course on the store tab. Otherwise, you can access the free resources and look into the details provided in the documents, videos and tests. All these options are for free on the free resources, free material tab, which you find on the side screen of a mobile app. Download the mobile app by clicking on the link which is provided to you in the description of this video. Thank you. So moving further, let us look into the further more questions. The next model of the questions related to packaging. We have looked into 3D-dimensional volumetric based questions. Let us have a brief discussion on some questions related to packaging as well. This is also a past UCEED question from the year 2024. Shown below are 2 stacked paper cups and a box with the dimensions. They have shown the dimensions of the box. If stacking is allowed, then what is the maximum number of cups that can be stored in the box without deforming? You should not push or compress them. Just stack them into this box. They're asking how many maximum cups you can fit into it. So when you're arranging the cups into this box, there are 3 ways you can do it. 1, you can place the cups on the base over here. Like you can stack the cups in vertical columns all along the base. That's one option. Other than that, you can also stack the cups in this direction, in this orientation. You can stack the cups in the vertical orientation. You can stack the cups along this orientation like this, like stacking them like this. So this orientation of stacking, that is one. Other than that, just the vertical stacking, that is one. And thirdly, you can also stack them in this orientation, like orienting the cups in this way and stacking it in the dimension of 12. So the dimensions are given 12, 16 and 6. 3 ways of stacking is possible. We'll need to check in all the 3 ways. Whichever way is giving you the maximum number of cups, that will be the answer. Let us start with the simple. Now this is just like hit and trial method. If you are able to logically think and come up with a say possible answer in the beginning itself, that will give you that will help us answer the question quickly. So for example, the number of cups, basically when you're stacking, if the length of those columns is high enough, then you can get more cups, because see, if you're along, it's in stacking questions for cups particularly, if you're able to stack them vertically in a tall line, you'll get more number of cups, because see, the increment for every one addition of cup, the increment is just half a centimeter. So it is always better to stack in long lines, you will get higher number. So stacking in this orientation will give you the highest number. However, if you want, you can check in all the three ways. For this calculation purpose, I'll show you the calculation for two ways of stacking. One, let us look into the stacking in the form of vertical orientation. Stacking vertical cups, vertical lines. Let us see how many cups we get. So let me draw the plan, the top view of this crate. This will be 16, this will be 12. The dimension of the cup is 4, so every cup will fit into 4 by 4 square. How many 4 by 4 squares can I divide this into? So you will get 1, 2, 3, 4. 1, 2, 3, right? 4, 8, 12, 16. So it is 16. So you can divide it into 4 columns and 3 rows. That's the plan. That's how the crate will look like from the top. So these many columns, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. I will get 12 columns of cups into how many cups can I stack in each column? So the height of each cup is already 4 centimeters. Half centimeter of increment for every one cup. So we are having 6 centimeters. So till 4 centimeters, I'll get the first cup. Then half centimeter, one more cup, half centimeter, one more cup. So this will reach us, give us a height of 5 centimeters. In one more centimeter, I'll get 2 more cups. How many cups am I getting? 1, 2, 3, 4, 5. I'll get a total of 5 cups. Till 5 centimeter, I'm getting 3 cups. In one more centimeter, I'll get 2 cups, 2 more cups. So I'm total getting of 5 cups in this 6 centimeter height. So 12 rows of 5 cups in each. So that will give me a total of 60 cups. If I'm stacking the cups vertically along this base in this plan, in this top view, I am getting 60 cups. But I told you, answer will be you'll get a highest number of cups when you're stacking them in long lines. Long lines will add up more cups because the increment for every cup is just half a centimeter. So let us see how many cups can you stack in these lines along this orientation. So firstly, if I draw the top view from here, top view from this direction, the crate will look of this size from the top. If I see, I want to see how many columns I can fit in, right? So this dimension will be 12, this will be 6. In 12 by 6, how many columns can I fit in? Vertically speaking, I can fit in 1, 2, 3. But horizontally, I have only 6 centimeters. So once I place one cup, there is no sufficient place for one more column here. So I will just have 3 columns of cups. In each column, how many cups can I stack? So I'm having a total of 16 centimeters. Of these 16 centimeters, 4 centimeters will already be occupied by just the first cup itself. How much is remaining after that? I'm having 12 centimeters. Half centimeter is the space occupied for every cup in the stack. So in 12 centimeters, I will get 24 more cups. Plus the first cup 4 centimeter. Right? So I'm getting 25 cups in each column. I hope you are able to follow. First cup is 4 centimeter. I have 12 more centimeters left, in which I will get 24 cups because the increment is half centimeter for every cup. So those 24 plus 1, I'll get 25 cups in each column. So there are 3 columns, 25 cups in each column. That will give me 75 cups. You see the number is increased drastically. Instead of 60, you're getting 75 now. In the other direction also, if you want, you can check, but that will give you a number less than 75. If you want, you can cross check from the third direction as well, just to be confident, because in the exam you don't want to have errors in such easy questions. It will probably take you half more minute to check on the other direction. So take that half minute, don't take risks. Cross check on the third direction also, and you will get an answer. Whatever value you're getting, you can cross check. But 75 should be the answer for this question, because that's the maximum number of cups which can fit into this given box of given dimension. So that's a question, simple question based on packaging asked in UCEED examination. Let us look into the next packaging based question. This was asked in SEED examination in the year 2020. So the figure shows top view. So it shows 2 views, they are saying. The figure shows 2 views of an object. What is the least volume of a rectangular box required to fix or required to pack 6 such objects? They are saying these objects, whatever shape, they have shown 2 views. They are saying that there are 6 such pieces. Those 6 pieces together how much is the minimum size of the box you require to pack those 6 pieces. They are saying least volume of the packaging, they are saying. Remember, in packaging, it is always ideal, you'll always get the least volume when you're trying to have uniform dimensions in all directions. That is, you should try and come close towards a cube. Whenever there's a question of least volume, remember this logic. Instead of having lengthy packages, it should always be close to a cube, the equating dimension on each direction. That will optimize the volume. However, it depends on the object you're packing also, because the voids also should be minimal. So minimal voids is the most important criteria. Second important criteria is bringing dimension uniform from all sides, bringing it close to a cube. So let us try to do the stacking for the given object. So in this particular case, if you look into, have some time and observe the dimensions, this is 10 by 10, it is square in plan. So in the square in this front view, and in the side view, if you see, there's a projection of cylinder coming out that is 3 centimeter in diameter. So this circle is 3 centimeter in diameter. The projection length, that is 3.5. So if you observe if you want to fit one more object on the other direction, let us say this is one arrangement. That's the object you have. The other object, if I want to fit it over here, so this is 3.5. This thickness is 1.5. This is given as 3.5. If I add one more object, 3.5 over here, I just fix it like this. So I'm trying to make it as cube as possible. So if I stack it on the other side, I just want to check if I can fit one more over here in this direction. Over here, can I fit one? That is something which you have to first see. So let me just see. Let me just see if the dimensions fit in to help me fit the third one over here. So this is 3.5. This also is 3.5, and this is 1.5. What is this total length? 3.5 plus 3.5, that is basically 7. 7 plus 1.5 and 1.5, that is 3. 7 plus, you are getting this total length as 10. There is a reason why they have given these dimensions. 10 is basically the side of the next piece. So I can for sure arrange the next piece over here in this orientation like this. This is 10. And is the depth also sufficient enough for me to fit this 3.5? Absolutely yes. This is basically 3, right? So if this is 3, the total distance is 10. If I subtract 3, I'll have 3.5 on the top, 3.5 at the bottom, and 3.5 is exactly enough for me to put in one more piece over here. So I can arrange the next 3.5. So this also 3.5 plus 3.5 plus 3, that is giving us 10, and I can arrange one piece over here. So this is a very compact profile with the least volume of voids I'm getting. So this is the arrangement for the first 4 pieces. The next 2, how can you make it as cube as possible? Fit it from the top and the bottom. So arrange the next one, the next 2, one on the top, one at the bottom. I have created a 3-dimensional composition over here for you to understand it or visualize it in a better manner. You can look at it in this picture. There are two of these articles, one behind the other, joined along this cylindrical form. The third one, the fourth one, I have not shown the fourth one so that you can see the arrangement inside. Once you're done with that, one on the top and one on the bottom. So what we need to do finally is just find out this overall volume. What are the dimensions? We need to observe that. So what is the dimension over here? If you observe this shape from here till here, this is just directly 10. These dimensions are all given in the dimensions. It's just units. They have not mentioned inches, centimeter or anything. So in the same units we need to give an answer. So this is 10. What is the total height you are achieving over here? You can disintegrate into smaller distances, which you know. This is 1.5 given in the question. The thickness of this slab, that's 1.5. And then you have this distance from here till here, that is 10. And this distance, that is 1.5. 10 plus 1.5 plus 1.5, this height is 13 units. This is 10, this is 13. And then the next L into B into H you need to do for this cuboid. So the depth we need to check. So from here to here it is already 10. I'll need to have 1.4 centimeters more, 1.5 units over here. This is 10 and 1.5 again over here. I did not draw the last one, right? If I insert that, I need 1.5 units more thickness over here. So this total distance is going to be 13 units. So the length, breadth and height, that is 13, 10 and 13. 13 into 10 into 13. So the volume for this arrangement, coming back to this question, volume for this arrangement will be 13 into 10 into 13. Length into breadth into height. In this plan, if I show you, this is 10 and along this direction it is 13. Along the vertical orientation also it will be 13 because I'm adding a piece at the top and the bottom. So 13 into 10 into 13, that will give us 13 into 13 is 169 into 10 is 1690. That should be the answer. So remember the concept in packaging. If you want to find out the least volume, the first rule, voids have to be minimal as possible. Second rule is that the packaging, the composition should be as cube as possible. That will optimize the shape and the volume. So that's about it. Let us move on to the next one. The next question, this is basically based on rearranging or cutting a solid. Let us look into this question. This is a past UCEED question from the year 2024. A wooden block of dimension 10 cm into 20 cm into 30 cm is cut into equal sized planks. Read the question very carefully. You are cutting it into equal sized planks. That's the first point given. Then the cut planks are stacked one above the other to achieve the total height of 100 cm exactly, not more, not less. If the minimum number of planks are cut to achieve this height, what is the volume of each plank in centimeter cube? So they are saying, cut it, arrange it to get a height of exactly 100 centimeter and do it by using minimum possible pieces. Minimum number of pieces they are saying, minimum number of planks you have to cut into to achieve it. They are asking what is the volume of each piece. So now this overall cuboid, it can be cut into smaller pieces in multiple ways to achieve a height of 100. Let us try to look into various possibilities which we can do it with. So the cuboid particularly, that is of dimension this is 30 centimeter and this is 20 centimeter. When we take it as 10, this is 10 centimeter, and the height is 20 centimeter, let us say. Now, any way you can take the direction or orientation of it. Now, it is cut into equal pieces to get 100. Now, if I want, now there are three possibilities. One, I can maintain the height of 20. Second, I can maintain the height of 30. Third, I can maintain the height of 10 itself. So I can maintain any of these heights to stack because all these pieces they are saying should be same, identical pieces. So I can cut into identical pieces along the length 30 like this. Cut it into smaller pieces along this orientation. That is one approach. I can cut into equal pieces along this direction, along the dimension of 10, where I'll get very thin slices. And otherwise I can also cut it into equal pieces along the height along 20. Let us try to do it ideally you need to check from all the three ways and see what is the minimum number of pieces you're getting, in which direction are you getting the minimum number of pieces. Let us see if I cut it along this orientation like this. How many pieces do I need to reach a height 20? So in this particular shape, this particular height 20 will be maintained. So I can stack 5 pieces one above the other. So I can cut it into 5 equal pieces, 1, 2, 3, 4 and 5. 5 pieces I can stack them one above, because this is already 20, right? The 20 is intact, that height. So I can place 5 pieces one above the other, right? I'll be getting 100 as the height. So in this orientation I'm getting 5 pieces. So this is a 2-level question. First you need to see which is the least number of pieces, in which direction are you getting the least number of pieces helping you reach that height 100. Next, let me see in the other direction. If I cut this, instead of vertical pieces, let me slice it horizontally now, along this height of 30. So in this, the maximum dimension is going to be 30. So one piece of 30 centimeter, above that I can place one more piece of 30 centimeter, that will basically give me 60 centimeter. One more piece of 30 centimeter, that will give me 90 centimeter. Is there any way to just increase 10 more centimeters after that? So 1, 2, 3, these 3 pieces, all of them have 30 centimeter height. This is 10 centimeter, this dimension is 20. So basically this 20 centimeter I can cut into 5 equal pieces. This is 5, 5, 5 and 5. So what is this total length? 20 centimeters. Now these pieces I can stack it to reach a height of 100. How? I can stack them like this: 30 plus 30 plus 30. This is 30, 30 and 30. And at the bottom of these, this last piece, I can just place it like that to get a height of 10, this dimension. This is 10, right? So I can place it like this. And then place the pieces of 30, 30 and 30. That will basically, I have not drawn it proportionately, I know, but I hope you are able to understand. That will give me a total height of 100. Now I'm able to do, if I'm slicing along this particular face, I'm able to do it in just 4 pieces. Let us see the slicing in the last possible orientation, the third. There are 3 orientations of slices. The third one is along this 10 centimeter dimension. If you are basically cutting it into equal shape. Now the key point over here is all the pieces should be of equal dimension. So like this. If I'm slicing into pieces this way, here also the maximum dimension is 30, so I can follow the similar strategy: 30 plus 30 plus 30, and then the last piece I can do the same thing. So what will be the length, what will be the dimension of each of this? If I'm cutting into 4 equal pieces, this will be 30 and this will be 2.5, 2.5, 2.5 and 2.5. The total will be 10. This height will be 20. Achha, can I achieve 100 exactly by doing this? 30, 30 and 30, that is fine. I can achieve 90. Plus the next dimension will be 20. I'll cross 100 if I stack it like this. If cutting like this and stacking in a similar approach, I'll not get 100 exactly. So this is not an option at all. Now least number of pieces is 4 pieces. Question they're asking, what is the volume of each plank? 4 planks we are having. What is the volume of each plank? You can clearly see the dimensions in this. The length is 30. The L into B into H. Length is 30 centimeter. Breadth here is 10 centimeter. This is 10. And the height, 20 centimeter of height you have sliced into 4 pieces. So each height is 5 centimeters. So the volume will be 300 into 5, 1500 centimeter cube. That should be the answer. Now whenever you have exact round figure based questions, you will not have any range in such questions. There's no range over here. 1500 should be the exact answer to get the marks for this question. So that's a past UCEED question again. If you are planning to have a self preparation, you can purchase a set of study material. We have developed a lot of workbook for the sketching part particularly, and you have books with a lot of practice questions for the reasoning and aptitude part. If you are enrolling into this 61-day lecture series also, you will get an access to our study material series, which you can study material set which you can use for your self-study and practice in addition to the lecture series. So all the resources you need for preparation, including the lectures, the practice tests, practice questions, and the books of best quality are provided from our end. All you need to do is utilize these resources and maximize the hours of time you put into your self-study, just focusing on practice, practice and practice. That's the only way to clear UCEED examination. Let us look into a few more questions at the end. A solid is shown in the figure below. The vertices A, B, C, D, E, F, G, H are form a 4 centimeter into 2 centimeter into 2 centimeter cuboid. The segments AI and DI are both of length 5 centimeter. This is from C 2019. The point I, C, F, G, P, all those are coplanar. They're on the same plane. What is the height in centimeter of point I from the base rectangle EFGH? They're asking us height from I to this height they're asking. Now in this overall height, you can break it down into 2 components. This part that is already fixed, that is already known. What is this dimension? 4 into 2 into 2 they are saying. So this is already 2 centimeters from the diagram you can observe. You just need to find out how much this remaining height is. To get this remaining height, you will need to visualize the given formation and see what in which area, in which direction can you apply Pythagoras theorem with the right angle triangle? I would say if you want to find, let me erase this for better understanding. Draw the right angle triangle joining this point I, the midpoint of this triangular face, this one, and point D. This one is a right angle triangle. So draw out this right angle triangle. I have drawn a lot of lines, so I think it's confusing. Let me draw it clearly again. Join in point D, point I, and draw up a perpendicular, this one. This. If you draw out this right angle triangle, you can apply Pythagoras theorem in this. The distance di is known. This height x I need to find out. This particular base from the midpoint over here to this, that I'll need to look into by drawing the plan. So if I know, so first let me draw it, visualize this right angle triangle first. This is basically the midpoint of the base of the triangle. Right? If I draw this right angle, this point over here, this is midpoint of the triangle base, midpoint of base of the triangle. There is a triangle which you see. Which triangle I'm talking about? The triangle I'm talking about is IBC. IBC triangle where BC is the base. So let me write it as midpoint of BC. BC is the base. So midpoint of BC, that's this particular point. This is point I. And this is point D. Joining these three, I can get a right angle triangle. In this, the distance from the midpoint of BC to I, that is something which I need to find out, x. Once I get the value of x, I will add 2 plus x, that will be my final answer. X I need to find out. Distance from midpoint of BC to D, that I need to find out also. ID is given in the question. DI, that is given as 5 centimeters. So this distance, what is this first? Let me find out. For that, I'll need to draw the plan of this cuboid. If I draw the plan of this cuboid like this, now this is where you have the triangle. Let me draw the other direction. Let us say this is A, this is B, this is C, this is D. Here, this is the midpoint of BC. I want to find out this distance from D to the midpoint of BC. How can I do that? Again, apply the Pythagoras theorem simply for that. What is the distance from C to D? It is 4 centimeters. This is 4 centimeters. And what is this height from midpoint of BC to C? That will be half of the length BC. BC length is 2 centimeters. So this will be 1 centimeter. So you can find out the hypotenuse easily. Root over 4 square, that is 16. Plus 1 square, that is 1. So this is coming out to, this distance is coming out to be midpoint of BC to D. I'm getting it as square root of 17. I hope you are able to follow the calculation. If any one of you is having any query, you can put out your doubts into the chat, or you can also reach out to us on a contact number. Enroll into our courses. Our faculty team will always be there to guide you through the preparation and clear all your doubts, whatever you're facing. However, let me repeat once again, it can be a bit tricky over here. I have drawn the plan. This distance is given as 4. This is half of BC, so it will be 1 centimeter because BC is 2 centimeter. From D to the midpoint of BC, that distance by applying Pythagoras theorem I have calculated to be square root of 17. Now the last step, I need to find out x. Apply Pythagoras theorem again. Square root of the hypotenuse is equal to square of the hypotenuse is equal to square of the base plus square of the height. So what is the value of x square? 5 square is 25. Minus 17, so that will be 8. So the value of x is coming out to be square root of 8. Square root of 8 is 2 root 2, so 2 into 1.414 it is. So it will come out to be 2.828. Now this is the value of x, 2.828. Because square root 2 value is 1.414. You'll have scientific calculator, but it is always easy if you remember the value of root 2, root 3, root 5, so on. Root 2 is 1.414, root 3 is 1.732. If you remember this, calculations can be very quickly done. This plus this, that's the total height from this to the point I. So the answer for us for this question will be 2 plus 2.828. So this final answer will be 4.828. That would be the answer for us for this question. Answer will be in the range. If I have the answer key with me, it's given as 4.80 to 4.84. The official answer key for this seed examination question is given as 4.80 to 4.84. That's the range, and this answer is exactly in the center of that range. You will get your marks for this question. Similar ranges are also given in the UCEED paper. So seed UCEED are of same level for some topics like this. So that's about it. There are some difficult questions as well. So let us look into these tetrahedron based questions also. We already learned the basics of tetrahedron. So I have also included few questions based on the concept of tetrahedron. Let us look into that and we can wrap up the lecture with that. So let us look into this. This is one of the most tricky questions. It was asked in UC 2024 paper. Shown below is a configuration of 4 solid spheres, each of radius 40 centimeter. Radius of each sphere is 40 centimeter, that are placed at 4 corners of a regular tetrahedron. So regular tetrahedron is a solid which is the simplest of all the platonic solids I told you, right? So at every corner, there are 4 corners in a regular tetrahedron. At every corner, there are having a sphere of 40 centimeter radius. The side of the regular tetrahedron is given as 120 centimeters. The centers of the sphere coincide with the corners of the tetrahedron. So these are the corners of the tetrahedron. All the 4 corners. They are having 4 spheres of 40 centimeter radius. Length of the side is given as 120. What is the radius in centimeter of the largest sphere that can be accommodated within the tetrahedron? They want us to fit a largest possible sphere into the tetrahedron. Generally, the largest possible sphere which can fit into the tetrahedron is called as the insphere. And we know the radius of the insphere already, that is root 6 divided by 12 into A. That's the radius of insphere. But they're not talking about insphere here. Just to complicate the question, they have already given some solid spheres already at the corners. That will reduce our available space. If there are no spheres, if they just ask you what is the maximum solid, what is the mole volume of the maximum largest possible sphere which can fit into the tetrahedron, the answer will be directly the volume of the sphere. You can find out the radius in terms of the length of the tetrahedron. This A value is 120. You can find out the radius and find out the volume 4 by 3 pi r cube, and they will get the answer. But then, however, they are only asking us the radius, not even the volume. So this will directly be the answer. Root 6 by 12 into A if there are no solid spheres at the end. But in this question, this is not the answer. Reason being, there are already spheres. Now, it is important for us to visualize how can we find out the radius of this particular sphere. First thing to know, the centroid of the tetrahedron is same as the circumcenter, incenter, and even the center of the sphere you're going to fit into, because it's a regular tetrahedron. See, the sphere which you fit in, that will also have the same center point at the midpoint, right? And luckily, we know the distance from the tip to that centroid. So if you look into this tetrahedron, from the tip to the centroid, we know the distance. This is the same center point for that new sphere you're fitting in. Now that sphere you're fitting in such a way that it touches these spherical surfaces also, right? And this sphere also has the same center. They have told us that the spheres, these 4 solid spheres which you're having, they coincide with the vertices of the tetrahedron. So if you find out, they're asking us this radius. What will this radius be? It is basically the distance from the vertex to the centroid. Distance from vertex to the centroid is nothing but the radius of the, from here till here, that is nothing but the radius of circumsphere. We know the formula for that. So what is radius of circumsphere? It is from vertex to the centroid. From this, you have to subtract the already existing sphere, this distance, this radius you have to subtract. that will give us the remaining radius, this one, right? Hope you are able to visualize it. Let me repeat again. Once you have the radius of the circumsphere, if you are able to deduct this particular radius, which is given to us in the question, 40 centimeter. If you are deducting that 40 centimeter from this, what will be left out? We will be having this distance. That's the radius of the largest possible sphere we can fit in. So basically, we will find out this total circumsphere radius minus the radius of this large solid which is already there. That will give us the radius of the solid sphere which can fit in. So basically, from the centroid to the sphere, I'll first find out the overall distance till the vertex and subtract this radius. Radius of the circumsphere minus 40, that's our final answer. So first visualize the given solid. Simple, straightforward, radius of circumsphere minus 40, that's the final answer. So we need to remember the formula for radius of circumsphere to answer this question, and you all know we have already discussed what is the radius of the circumsphere. It is square root of 6 upon 4 into A minus 40 centimeters. The length of A is given in the question as 120. Substitute that over here. So the answer for this question will directly be root 6 by 4 into A is basically 120 minus 40. So you can use your calculators to do this. 120 upon 4 is 30. 30 into square root of 6, that is 73.48. Subtract 40 from it, minus 40, 33.48 is the answer we are getting. 33.48. It is in centimeters. So that's the maximum radius of the solid, the radius of the largest possible solid which can fit into this configuration, 33.48. If I have the solution, let me see if I have the answer key range with me. No, but answer key will be in a range. You can check the UCEED 2024 answer key on the official website of UCEED. The range, there will be a range plus or minus some values, but this is how you solve it. Radius of the circumsphere minus 40. First visualize, then apply the logic. In tetrahedron, I already told you the formula for radius of circumsphere, radius of insphere, total space height of the tetrahedron. These three I told you are important. If you remember these three, you can always easily find out the volume and the surface area of tetrahedron if required. That brings us to this question. This is a past UCEED question from the UCEED question from the year 2023. Let us look into this one as well. A triangular pyramid with equal sides can be flipped on its edges without slipping or sliding, as shown on the left. So there's a figure. It cannot be slipped or slided. It can just be flipped along the vertices. They're flipped along the edges, they are saying. What is the minimum number of flips needed for the pyramid to reach the finish line from this position? So you need to flip it and reach it, make it reach the finish line. They're asking how many minimum flips you require. So let us try to do that. You cannot flip it along the vertices. You have to flip it along the edges. So to make it reach to the finish line, the first flip will give us something like this. This is the first flip. I'm flipping along this edge. I'm just flipping along that edge. I'm not reaching any further, but this is the first flip, which is making us reach over here. This distance we need to first find out in this. So the plan is an equilateral triangle. So what is the dimension of this equilateral triangle? Over here it is 30 is the side. Equilateral triangle, length of the side is 3. So what is the height of this equilateral triangle? This is the height of the equilateral triangle, right? So height of the equilateral triangle we have already discussed in the previous lecture. Height of the equilateral triangle is given by root 3 by 2 into A. So that is root 3 by 2 into 30. How much is root 3 by 2 into 30? You can use your calculators for that. Root 3 is 1.732. 1.732 into 30. Divide that by 2. 25.98. You can round it off. Slight plus or minus few digits after decimal. That's perfectly fine. So this distance is 25.98. Right? Now, the next time I flip, I will directly reach this point. That's the second flip, which is making me move further by one more height of the triangle. That is 25.98. Now you observe that for every flip, every time you're reaching to the next step, you're going further by 25.98. How many times do I need to do that to reach 135? Approximate idea, 135 divided by 25.98. I'm getting 5 point something. So at least 5 times I need to move further like this. Right, so once I reach 25.98, the next third flip, flip it along this particular side again. I'll not reach any further, but I'm creating a base for the next flip. The next flip, I will reach to this 0.4. Now this is again 25.98. Right, that's the fourth flip I have done. We need to count the number of flips, minimum number of flips required. The fifth flip, I'm again reaching over here, flipping over there. Then the sixth flip will again make us reach furthermore 25.98. The next flip, it will not take us any further, but you're creating a base for the next flip. That is 7. This is number 8. Eighth flip is making us reach 25.98 again. So we are done with 1, 2, 3, 4, 5 flips. 5 flips. What is the height we have reached till 5 flips? 25.98 into 5, 129.9. This distance till now, that is 129.9, almost 130 centimeters we have done. Centimeter, whatever units they are talking on, no units given, so just measurement unit, it can be any units. 129.9 is done. So next flip, this is flip number 9. The 10th flip, now I'm just left out with 135 is the total distance, right? Just 5 more centimeters. The next flip, I will touch the finish line. I'll actually cross the finish line by 20 centimeters. That's the 10th flip. I'm crossing the finish line by 20 more centimeters because I'm overlapping it already. So I've reached my finish line. So the minimum number of flips required is 10. That would be the answer. In such cases where there is nothing to round off, answer will not be in a range. You have to give the exact answer. Answer should be given. So 10 should be the exact answer without any rounding off. So that's how you do it. Number of flips, find out the height and see if you're crossing 135 and when you're crossing 135. That's the trick here. To solve practice questions of similar standard for UCEED seat preparation, make sure you download a mobile app. Practice tests are uploaded in the tests. I already showed you where to access the free material on our mobile app. The link for the mobile app to download, that's given in the description of the video. If you want further guidance and have an extensive preparation for the complete lecture series, you can enroll into it, purchase the series for the link for which is already given in the description of this video. Thank you for watching this video. Stay subscribed to this YouTube channel for important updates regarding seed and UCEED preparation, and I hope it was a useful lecture for you. Thank you.
KP classes dedicated to excellence.